about the molecular dynamics simulation and like how some of the related to the LAMPS and some MDs limited software also. So in this lecture, I will discuss how we can use LAMPS for a particular problem. So I'm Vijay Joel, a research scholar under the supervision of Dr. Suresh Kondalwal in the Applied and Theoretical Mechanics lab. So already we have seen the introduction of molecular dynamic simulation. So I will show you the workflow of the LAMPS and how we can build the LAMPS input script for a particular problem. If time permits, also I will show how we can build the nanostructure in the IISER software. So basically, in molecular dynamics simulation, what happened? So there is a force that is a interatomic interaction between the atoms, or like we can see here the sketching of bonds and angles. So this our main aim to obtain this force using the LAMP. So once we have the force, then from the force using Newton's classical mechanics second law, we can obtain the acceleration. And then using this acceleration, various algorithms were available, like velocity or like method, or any other methods are available. So using we can obtain the positions and new velocity, and then using this new velocity and position, we can obtain the all parameters according to our desired output. So that is the part of LAMPS that LAMPS performed in the background. So this is just simply overview of MD. So these are the parameter during the input script. I will explain what parameter we have used to solve the problems. So yeah, so that is the overflow of the LAMPS. So LAMPS is a freely available software that is called large scale atomic molecular massively parallel simulator. So there is a four division of that script. First, like initiation of simulation, then atom definition, then settings and runnings. So this all the division of that LAMPS script I will explain in the input script. How we will define the boundary condition, how we recall the data file in the setting. That is the main our physical problem. How we can solve the physical problem using the applying this simulation parameter. So what, like I will tell you how this it will work simply. So first we will create a data file from any available modeling software, that is Nano Engineer, VMD, some make use Material Studio also. So from this real, we will got this real structure and we will convert this structure into the data file. Data file that is just we have X, Y, Z coordinates of the particular atoms. And then for like potential field, we will also choose a potential field in such a way that it can be applicable for our system. Like if I am simulating boron nitride nanotube, so it should have some boron nitride parameter coefficient. Like earlier in the lecture given by Dr. Kondalwal, he shows that different interaction between the atoms, and that he shows some the coefficient between the some stretching of bonds also. So this coefficient already available in this potential file. Also, we have to define the time step, temperature, pressure, strain rate according to our condition. So, and this last step is running. So there is a two, we can run the during running, we can apply our boundary condition in two types. Either we can apply our boundary condition to the simulation box, or also we can apply our boundary condition to our system also. Sometimes the system was that much complicated, so we will not be able to apply our boundary condition to the on the system. So what we will do that we will apply our boundary condition to the simulation box, and then simulation box is already attached with our structure or system. So once we define the simulation or we apply the extra extremity to the box, that will directly apply to the our structure. So this is the problem I am going to cover. So this is uniaxial tension. So we can see that. So in the during uniaxial tension, we will fix the one end of the boron nitride nanotube. Yeah, the problem we have taken, the material is boron nitride nanotube, and So one boundary we will fix the, and other boundary we will like allow to atoms on this end, like they constant move towards the like to deformation. So we will get the failure point, or like we will deform in such a way that we can get a failure phenomena of the nanostructure. So now I'm showing you the basic things for LAMPS in the real problem, how we can so do. So yeah, so for LAMPS, it is visible my screens, everyone.
Yes,
Yes,
sir.
sir.
Yeah. So here is basically three files we required to run the simulation. So here we can see that this is the potential file, and this is the data file, and this is the our main input script. So I quickly I will show you how, once like we don't know anything, then how we can do that. So like first we need a data file. So I can tell you how we can create a data file. So just we can go to the nano engineer here. So already in the previous lectures I explained that how we can create the nano tube. So here, like I have taken a boron nitride nanotube. So we can create our nanotube in according to our specification, and then we will export this nanotube in the format of protein data bank. Yeah, that is almost all software can use this type of file, that is protein data bank, and from this protein data bank we will convert our data structure. So in nano engineer, also like in previous lectures I explained that, so a single defect can also affect the fracture of the our structure. So we can also create the defect using this software. Like if we will take, so we can select just like a atom and we can delete this atom. Also we are using some other methods, we can like add other defects also, like stone wall defects, add on bond defects. So different defects we can create here, and we can uh, make our system to be just equivalent to the real experimental structures. So yeah, so this from here we can convert into the protein data bank. So I already have a protein data bank created, that we can, so export protein data bank, and so we can give the name PNNT. Also, and we have to, before saving, is that we have to minimize the energy of the system also, minimization of the energy. So this is the tool we can use. Here is a tool, and using this once here we got the done, then it means that energy is minimized. You have already have seen that the atom are displaced from their position, and according to their interatomic interaction, their energy was minimized. So from there we have created the data file. Yeah, so this is the, like I have already created data files. So we can see here, so that is the format of data file. So first line we have seen that this is just comment. So we have to define the number of atoms. Like I have, my system is having 410 atoms, so I have defined just like you can see there is 410 atoms. So the first line is we have to define the number of atoms. Second, how many types of atom you are using. So I have just defined we have using two types of atom, that is boron and nitrogen. So yeah, and then we have to define the simulation box. So from the universe we have to separate our systems. So we just define our simulation box. So we have to define simulation box in a such a way that our during deformation also our system should not cross the boundaries. Like if you can see here, like this is our system, so like we can create so here is our system, so we can create our simulation box such that, so maybe large simulation box outside the our system. So during complete simulation, the extra stimuli will be performed on this simulation box or inside this simulation box. Then second is we have to define the masses here. So like already in previous lecture, sir shows that. So LAMPS will not read the direct command like boron or nitrogen atoms, that symbol. So we have to convert into the binary form like 1 or 2. So like we have defined the nitrogen as a 1, and yeah, boron atom is a 2. So and also we have defined the masses of the atoms, like say nitrogen having mass of 14 MeV and boron is having 10.81 MeV. So that we have defined, and then simply what we will have to define the our data points. So this first is number of atoms, second is which atoms, like 2 indicate for nitrogen, 1 indicate for boron, and this is the x y z coordinate. So our data file is now our data file is ready. Now we need potential file to perform to obtain this interatomic constant. So whenever we install our software LAMPS, here we will get all the things. So this is very informative things they have given here, everything. Like if I will tell you, they have given many example also, so you can run these examples quickly from this uh, their installed software also. Like here they have how to calculate elastic constant, so they have given this example. So many examples they have given that. So from like if we are starting the LAMPS, so we can run one of the example from in LAMPS itself, and then we can modify our problem according to the our problem. And there is yeah, here I am talking about the potential files. So many potential files available here. We can see if our like if we are using boron nitride the nanotubes, so our nanotube having boron and nitrogen, so we need such a potential file. They have the coefficient related to the boron and nitrogen. So this is a potential file we can use. But yeah, also if your system is having carbon nanotubes, and then you can use ch rabo and ergo potential also. Ergo is also available here. Yeah, if you want to use rear X potential for Intrex, this rear X potential used to perform your to calculate the charge interaction also. So some simulation make use this for rear X potential. So our aim, like for potential, we need not to worry too much. So already all potential, yeah. If you want to modify that potential, you can do simply like this is the potential. If I want to modify this cutoff, so this is the in each and every interaction. If I want to, this is the cutoff. So 1.95 R plus D, that is this is R and this is a D. Here you can see. So these are the parameters related to the potential file. So this is R and this is D. So if you want to change this parameter, you can change according to like already sir explained his lecture that one should change their their cutoff distance according to according to their problem. Also for optimization also sometimes we need to, because not each and every system having same cutoff distance, so we can change this cutoff distance from here. So this potential file easily can modify, but right now we are using whatever the readily available potential file for our simulation. So we simply just copy this potential file and we will put to the, like I have created new folder and we will put one by one. So I have put this potential file and we will obtain this data file directly, whatever I have created earlier. So this is a data file. Now third thing, we need input script. So according to our problem, we will see I have input script for tension.